Okay, hi everyone. Welcome to the second lecture, the first sort of real substantial lecture in this series on introductory statistics aimed at social scientists. Here are some announcements that follow for our class, the one I'm teaching, but I'll start with kind of an overview of what we'll talk about in this lecture before going further. So we'll start by reviewing some key mathematical tools, all of which are pretty important for basically this level of math. We don't really need calculus in this course, although it's oftentimes helpful. We don't really even need a whole lot of algebra 2, but at minimum, a firm grasp on algebra of the sort that you probably learned in the seventh, eighth, or ninth grade is going to be pretty important. Then we'll talk about some basic distinctions among types of data. So we'll go over some terminology that might seem like jargon, but it's actually linked to some fundamental and pretty interesting ideas, although ones that can be a little bit challenging if you don't really work through them. So we'll talk about the distinction between qualitative and quantitative variables, and we'll subdivide them. Qualitative variables are subdivided into nominal and ordinal. Quantitative are technically subdivided into interval and ratio, but that won't be as important for us. It turns out that most of the graphical and then later numeric techniques that we'll learn work for only one type. And then we'll talk about the type of distribution of qualitative variables. Pardon me. We'll go over pie graphs mostly as a negative example, and then we'll talk about some reasons to prefer bar graphs. We'll talk about the distribution of quantitative variables, and we'll go over histograms and box plots. Box plots, we need to do a little bit of basic numeric analysis before we really understand them, but we will talk about histograms. And I'll also at some point discuss the distinction between discrete and continuous quantitative variables, which will be important for understanding the distinction between bar graphs and histograms in a little bit more detail as well, since bar graphs can work for certain types of quantitative variables, but are not a great choice for certain other types, and we'll see why a little bit later on. Then we'll go over a caveat with time series plots, which the book that we're using, Moore, Knotts, and Fligner, discusses and then kind of drops. But one, it's my area of research is in time series analysis. And even though we won't get to that in this course, understanding what a time series plot really is will hopefully give you a better grasp on what some of these things above are. And then finally, as a bonus, we'll go over some interesting sort of historical examples of graphical methods. So a lot of great sociologists were also kind of pioneering data visualization people. And so hopefully we'll have some time for that. Those are some announcements for our course. I'm going to skip over those in the interest of making this video series hopefully something that can sort of stand on its own. So let's review some basic arithmetic and algebra. So I'm going to just show you how to do all of these problems here. And hopefully you can pause the video here and try them on your own and see if you can get the same answer. But I did want to discuss the way to solve for them. So the first one here, this is 6 times. And this time symbol here might look a lot like an X. But generally in my slides, you'll see X written like this here. This is just the way that they're distinguished in LaTeX, which is a mathematical notation software. Or I actually run what's called MathJax, which is a alternative you can run through Python, but no need to get into the details there. So X and this time symbol might look pretty similar. You'll need to use context clues to tell the difference, but hopefully these are visually distinguishable enough. And sometimes we'll use asterisks to indicate times as well. You have probably seen tons of notation for multiplication, so this is maybe just worth a preliminary note. 2 other kinds, you might see a kind of mid-height dot here. We won't use that in this class because in linear algebra, which we don't really directly cover in this class, but which is related closely to this class, and I'll often mention some results from it, that means something unique in linear algebra. It's called the dot product, so we don't want to confuse it with that. And then finally, you'll also sometimes just see numbers smashed together. So I could have just written this 25 and then smashed up against this set of parentheses here. And we'll see that pretty often too, but I thought we would start out easy here. So what does this tell us here? Well, hopefully you remember the rule here. You can either just add these 2 numbers up and get 8 and then multiply by 6. Remember your times table, so it's 48. But note that you could also distribute this as well. So you could write 6 times 5, which is equal to 30, 6 times 3, which is equal to 18, add them together and get 48 as well. one way to see that is if you think about multiplication as being fundamentally analogous to the process of taking the area of a two-dimensional figure, like a rectangle. So maybe you've got a side here that's got 6 and a side here that's got 5 and then 3. And you think about finding the area of the entire rectangle, well, then it seems pretty intuitive that you would do 6 times 5 to get the area of this one here, and that's 30. And then you would do 6 times 3 to get the area of this one here. And then since the rectangles are presumably touching, you can just add them up and get 48. So that's the reason that the law of distribution works. This one here, we need to remember what an exponent is. So an exponent says, for any old exponent k, it says take the number that is the base and multiply by itself k times. So here k is equal to 2, and that instruction tells us to multiply 2 by itself twice, or to multiply it by itself once, to be most exact. I was actually misspeaking there. Multiply 2 times 2, so there's a twice operation, but you get what I mean. Basically, we also refer to the second power as squaring, the third power is cubing, and after that, we don't really give them very standard names. But exponents are really important in this class, so you will need to get familiar with those again if you don't remember them. So 5 times 2 squared, well, 2 squared is 2 times 2 is equal to 4, so 5 times 4 is equal to 20. Now we'll come to negative exponents here. Negative exponents can seem a little bit scary. Here's how I like to think about what they mean. So remember that powers are, generally speaking, pretty easy to understand for 1 and up. So 5 to the first means multiply 5 by itself, but like only one time. It's a little bit hard to kind of justify that, but you can just sort of think like basically take 5 and multiply 1 by 5 a certain number of times, and then in that case it's just 1. So that might be a way to remember that, is anytime you're multiplying by an exponent here, you can say, okay, well, it basically means take 1 and then multiply 1 by 2 times 2. So 5 to the 1 means take 1 and then multiply by 1, 5. And then similarly, 5 squared is 25, 5 cubed is 125, and so on. Not too bad. But then we get to the problem of 5 to the 0. And 5 to the 0 will help us understand negative exponents. So what is 5 to the 0? Well, hopefully you recall, it's a kind of interesting fact that any base to the power of 0 is actually equal to 1. And you can kind of use the trick that I just mentioned, although I'm not claiming it's very rigorous, but it's maybe a nice way to remember it. If you say, okay, well, take 1 and multiply it by, and 5 to the 0 means don't put on any 5s. It doesn't mean multiply by 0, because 0 is not a multiple of 5. It just says don't add anything else. Just take 1 and multiply by, well, nothing really, but not nothing in the 0 sense, just don't multiply. So that's one way to think about it. Again, I'm not claiming that's the mathematically correct way to think about it, but it might be helpful. So any power, any number to the power of 0 is equal to 1. So then what we can remember is that the way we handle fractional exponents, so like x to the 6 over x to the 2, hopefully you remember that the rule there is to subtract exponents, because if you line up all the x's, you'll have 6 x's in a row. And I really should have gotten my iPad out for this, but maybe another time. So you'll take those 6 x's in a row, and then you'll divide them by 2 x's in the bottom. And you'll notice that 2 of the x's cancel. And it may be useful in a way for you to try to translate that and see that it works, even though you can't see me doing it. So write out, instead of, x to the 6, just write out x times x times x times x times x times x. And then in the denominator, don't write out x squared, write out x times x, and then do standard cancellation. And you'll see that you end up with x to the 4th. So the way to understand negative exponents then is to recall, okay, so how would I get 5 to the negative 1? Well, one way to think about that is you could just have 5 to the 0 over 5 to the 1. And if we follow our subtraction rule, we would get 0 minus 1, which is negative 1, and then take 5 to that power. So what would that actually mean, though? Well, 5 to the 0 is equal to just 1, and 5 to the 1 is equal to 5. So 5 to the negative 1 is the same as 1 over 5. And then when we go ahead and multiply that out, we would get 25 times 1 over 5, or 5. Negative exponents are somewhat important in this class, and I encourage you to get comfortable with them as part of the process of just getting comfortable with exponents generally. How would we solve this next one? So one thing to remember is that, so first of all, what does this operator mean here? This is the radical, and the radical is an operator that tells us to take the square root of something. And so here we are saying, maybe one way to think about how to solve this is to remember the power of the equality sign. So when I tutor high school students in math, like when I'm tutoring people that are learning this for the first time or relearning it for the ACT, I remind them that the equality sign is very powerful. So what this means is that no matter what x is, and no matter what any of the heck this stuff is on the left, it's equal to 8 by definition. So that means that all the regular rules of algebra apply. So for instance, if we know that two numbers are, or two sides of an equation are equal, we can square both sides, right? Because let's say we just have 2 equal to 2, which is trivial, but it's true. So 2 squared is equal to 4, and on the right-hand side, we have 2 squared equal to 4. So we're allowed to square things that are the same, even though squaring is not a linear operation, which sometimes freaks people out because they're like, well, it's not like, I remember I can multiply both sides by the same thing, but can I really square both sides? And the answer is yes. And maybe another example you could think of would be to say, write like 4 is equal to root 16, for instance, right? And then square both sides. So you square 4, you get 16. And then what does it mean to square something that is under a radical sign? Well, if you have the square root of something, and then you, which means that it is basically what you, basically what number when squared gives the thing inside, then that operation just undoes the square root operation. So what does this fundamentally tell us here? This tells us that if we square this, we'll get x over 49. That's literally what this operator means. So it says, whatever number this thing is here, whatever number k is represented by this whole operation, will be, when squared, equal to x over 49. So you can think about this as in itself almost like an equation. So how can we solve it? Well, again, we can square both sides if we want, because we're saying by definition, whatever this is, it's equal to 8. We don't know what x is, but this whole equation or expression is equal to 8. So let's square both sides. We get 64 over here. And then here we're just going to get x over 49. And then what we'll need to do is multiply both sides. And my mental math is actually not quite that good. There are various tricks we can use, but those aren't going to be very important for us. So what we want to do, I'm going to pull out my hand calculator here, is then multiply both sides by 49. So we'll multiply 49 by 64, and we get 3,136, or 3136. And we can check that as well, and it may be useful to check it. So you'll, to check that, take 3136, divide by 49, and you'll get 64. And then hopefully you remember from basic high school math, the square root of 64 is equal to 8. Now let's try number 5. Those of you that have any prior experience with statistics will know that we'll come across this quantity soon. This is known as a z-score or a standard score. And manipulating this very simple algebraic equation, this means any old observation, this means the mean of the set, and this means the standard deviation. Manipulating this equation to solve for x, sigma, mu, or z is actually pretty important. By the way, this is mu. It's a Greek letter that makes the M sound. It kind of looks like a messed up M. You can almost think about it like a really cursive or fancy M. So don't think about it as U because that's kind of confusing. Remember, this is a Greek M, and it makes the M sound as in mean. This is sigma. It also makes the S sound. You can kind of see that it looks like a messed up S, not really. And unfortunately, capital sigma looks like an E. We'll meet that soon enough. So yeah, it's a little bit hard, but if you just remember that this is sigma, it is sigma for a reason, because it stands for standard deviation. Anyways, how would we solve for x here? This is not conceptually maybe even as challenging as what we saw above, but I found that people oftentimes solve with very inefficient algorithms that lead them to make mistakes. In particular, something that a lot of people do here is try to turn this into x over sigma minus mu over sigma, and then somehow go from there, like by moving over mu over sigma and then multiplying out. But it is really just not a great idea, because In general, to solve for a given variable, you want to move over you want to get everything simplified as much as possible on that side. And in general, equations that involve one side being, or like any side of an equation that involves division is not usually optimally simplified. So here, the simple thing you want to do is just move over the sigma. So we'll multiply both sides by sigma. We get z sigma is equal to x minus mu, and then add mu to both sides. So we would get mu plus sigma times z, or z times sigma, doesn't matter because multiplication is commutative, is equal to x. That same set of principles about solving in efficient ways applies to question number 6. So we'll see soon enough that this is something that is a particular form, in a way, of what's called the margin of error, right? So we already met the margin of error once, and we'll see later on, although not for quite a while, that this is kind of an important tool. So what we want to do here is, again, try to simplify as much as possible before we do anything crazy. Now, we have the variable of interest in the denominator here, which is a little bit frustrating, but I'll show you that there's a simple trick. So we'll first move over the z by dividing m by z. So we get m over z is equal to sigma over root n. Right? Now, you might wonder, well, do I need to maybe multiply both sides by root n and then divide out? And you could do that if you want, but a cool trick you can use is that m over z equal to sigma over root n. You can just flip both equations, and that also has to be true. Let me give an example of that again using a simpler case. So let's say that we know, for instance, that 3 over 5 is equal to 12 over 20, right? So in both cases, we just multiply top and bottom by 4. So 3 over 5 equals 12 over 20 because 3 by 4 is 12 and 5 by 4 is 20. Now, you can also see that that has to be true when you flip the 2 over. So 5 over 3 is equal to 20 over 12. And hopefully it's immediately clear, but even if it's not, just divide 20 over 12 both by 4, and we get 5 over 3. 5 over 3 is equal to 5 over 3. So we can, generally speaking, if we have a proportion, which is formally speaking a statement that two ratios are equal, by definition, then that means that you have to be able to flip them over and get the same equation. So let's do that here. So then we would end up with z over m is equal to root n over sigma, and then we can just multiply z over m by sigma. So z sigma over m is equal to root n, and then we would just square the left-hand side, which would give us z sigma over m squared is equal to n. And by the way, I'll remind people that in these slides, you can see the answers here. So you can check our answers before. You may not remember these off the top of your head, but we had 48, 20, 5, 31, 36, z sigma plus mu over here, and then z sigma over m squared, so just as we found by hand. So that's a little bit of review of some basic algebra and arithmetic, really. But now we need to take a look at something that might be a little bit more challenging, which is index and summation notation. So let's refer to a set of x's that denote n numbers. And you can think about this as being like a collection of observations that we want to call x. And you can think about them as basically being draws on the same variable. So like, let's say we let x represent education, and we're trying to get at the mean level of education in a place, and we survey a bunch of people. You can think about each person as being in themselves a random variable, and they all come from the same population. So they're what are known as identical and independently distributed random variables, assuming that you survey people at random. So you don't survey two best friends, you just call people from the telephone book in the old-fashioned way of thinking about it. And if they're all drawn from the same population, they're identically distributed, which might sound a little bit confusing, but what that means is that for each, like, let's say you plan to call 20 people, and you write down x1, x2, up through x20. Before you actually contact those people, so while the x's are still random variables, they all come from the same population. And in principle, they all have the same sort of distribution in the sense of like if you did the experiment over and over again, as you're doing 20 times here, it gets a little tricky because we're not, assume that you could even call the same person twice just by coincidence. You probably wouldn't do that in reality, but let's assume you could. Then what that means is that every time you call someone and ask about their education, in theory, you are taking them from sort of the same distribution. So like the same set of possible values basically governs these sample draws. That might seem like a lot, but I found that a lot of times summation notation sort of strikes people as somewhat pointless until they see like a reason to think about it this way. So why would we bother writing x1, x2, and so on? Well, if you have a variable x that just represents education in a very abstract sense, but then you end up with an actual set of data, and you have someone, person one's education, person two's education, at that point, those are no longer random variables. They're realizations of random variables, but it's still helpful to think about them as all measuring the same thing. So let's say we wanted to define the sum of education in the sample. Now, that doesn't immediately seem to make sense because why do we care about what the total education of 20, or in this case, 5 people is? Well, we don't really, but you'll see later on and soon enough that we'll often want to take the mean education. And to get the mean, we first take the sum. So this is actually pretty useful. So here, to sum up x1 through x5, we're going to write this capital sigma here. And I mentioned before that capital sigma looks like an E, but this actually is a big S in Greek, ancient Greek, and I think contemporary Greek as well. And what this tells us is sum from I equal to 1 to implicitly I equal to 5, although we never write the I equals up here. And sometimes you'll just see 1 to 5 here, and sometimes you'll just see sigma where it's obvious, although we oftentimes take partial sums, so there's a reason that these are written here. Basically, what this tells us to do is write down person 1 here, and then add that to person 2 and then person 3 until you get to person 5. So anytime you see this summation notation, what this is telling you is sub in person 1's value, then add, then add, then add until you get to person 5's value. So another way to say that that's simple is this means take x1 plus x2 plus x3 plus x4 plus x5. I wanted to note there's many summation properties that are useful, but one that we'll use pretty often is that summation over a constant yields n times that constant. So let k stand for a constant. It's not a variable here, even though it's a letter. It just means some number that's any old number. Usually you'll see capital Roman letters for variables and lowercase Roman letters for constants, and in particular k very often means constant. It can also mean the number of variables in a data set, which is also a constant. It's not itself a variable, at least in almost all cases. So what this means here, when we write down I equal to 1 to n here, that might seem a little bit confusing because there's not a subscript here. But what this is really telling us is when there's not a subscript, whoops, sorry, my Google Slides is very sensitive to like touches. You'll see this happen pretty often. What this is telling us is basically just sum up k n times. So this is equal to n times k. And we'll see an important use of that soon enough, but I'll just kind of foreshadow it here. So you can think about the sum. Well, actually, let's put that off for a moment. I don't want to get too often in the weeds. We'll come back to that. So let's take a look at an example here. So let's say that we're given the instructions sum xi in this case. And by the way, this is kind of hard to tell if this is capital or lowercase, but anytime you see subscripts, that means that it's a variable, meaning that it's a vector on which you have multiple observations. So if you ever see a subscript, you also know that that's a variable and not a constant. By the way, if some of those things don't totally make sense yet, don't worry about it. We'll get an intuition for it as time goes on. So what do these instructions tell us here? Well, what they tell us to do are start with person 1. And if you don't have numbering of the people in the data set, you can just put them in any old order and then implicitly assign them a number. But we might also, and we often do, have variables that indicate which observation someone is. So here we've got this variable I, and that just indexes all the people. It just tells us who is person one, who's person two, and so on. So this row is person one, this row is person four. And basically what this tells us to do is go to person one, find their value for X. You can assume this is years of education, seems plausible. And then go up till N. And when N is not further specified, it is the total number of observations. So here there's 4 observations. And so what this tells us to do is simply add 10, 11, 14, and 15. And I'll show you a kind of efficient way to do that mentally. So these add to a nice number, 25. And I find that by just looking for 1 and 4, they equal 5. I see another 5, so that's convenient. Then 25 and 15, the 5 sum to 10, 2 and 1 sum to 30, add another 10 is 40. And then we just add an even 10 at the top, 50. So that's a way to organize mental math that might be useful for you. And so the answer to this will be 50. Then we can also write the sum with a 1 over n in front. And when we do that, you might remember that the sum of observations over the number of observations is another way to write the mean or the average. And so we'll see in our lecture after this one that this is a convenient way and a very common way to write the sample mean of a data set. And we can check our answers here. And I'll give you all a moment here to check your work. You can see we got 50, and I guess we didn't solve to the end here, but 50 divided by 4 is indeed 12.5. Long division isn't really important for us, but the way to remember that is you want to picture 50, think how many times does 4 go into 5? 1, then multiply 4 by that number we got, 1, subtract it from 5, bring it down, then bring down the 0, so that gives us 10. How many times does 4 go into 10? Twice. Then do the same process, multiply, so 4 by 2 is 8, and then 10 minus 8 is 2, and then 4 is not large enough to go into 2 evenly, so we bring down a 0, 4 goes into 25 times, but we have to remember that we added the 0 after the decimal, so we have 1 to decimal 5, or 12.5, so that's how we do long division. It's probably a good idea for people to try to remember like why that really works, but it's not important enough for us that we will go into it in this case. Okay. I guess now I'll go ahead and mention the trick I was saying before about constants here. So one thing we can recall is that if the summation over a constant is just equal to n times that constant, sometimes it will be convenient to think about basically that constant as being the sample mean. And then what that means is that this is the sum of all the observations, and then we can rewrite that over here using the sum over xi, which is kind of useful. So n times the sample mean happens to be equal to the sum of all observations, so then we can sub in here, this would be xi. But we'll come back to that trick later on. Here's some material about function notation. Functions aren't really important for us to know in too much detail for this class, but I did just want to mention a couple of kind of concepts here. So first of all, in general, when we see things like this, y is equal to f of x, we say y is a function of x. A function is really just a rule that associates an input, sometimes called an argument, with some output, so it returns an output. So here, f is a rule that maps x to y. In other words, we put in some x and we get back some y. Now, the function here is not specified. We just wrote f of x, but f of x needs to be given in more precision. So a very common example would be that the function is just a linear expression. So for instance, y is equal to f of x might be replaced by y is equal to mx plus b, where the function f of x is mx plus b, where b is some constant, m is some slope, and this would give us the equation of a line in Cartesian or two-dimensional space. There's a whole lot of kinds of functions you can have. You can go from single inputs like we just saw to a list of inputs, and that can output lists or just single outputs. And we can even have mixes, and sometimes we can have matrix inputs and get matrix outputs. we're going to focus on pretty simple linear functions in this class. So we will have, technically speaking, multiple inputs, although one is just a constant, and we'll have just one output. Now, these will stand in for many different possible people. So in a sense, they refer to lists, but the idea is that you can think about this equation as just applying to individuals. Again, we'll come back to that in some detail. One thing I did want to note is that in this class, we'll denote generic linear functions like this, y equal to mx plus b, with this notation that's somewhat more standard. So capital Y representing a random variable is equal to beta naught, which is a constant, plus beta 1 times x. Again, that's much more important down the road, so don't worry about it too much for now, but I just wanted to call your attention to that. So let's talk about some actual data. So we need to learn some basic number theory. The key pieces for today include definition of a variable, and then we'll talk about two types of variables, quantitative and qualitative, and we'll often refer to them as quant and qual variables, at least in writing. We'll talk about some subtypes of qualitative variables, nominal and ordinal. Then we'll talk about some quantitative subtypes, interval and ratio. And we'll also talk a little bit about continuous versus discrete variables. So that's the agenda for today in broad outline, and then we'll go over some graphs. So first of all, we need to talk about what variables are. And it might be easier to start actually with not what variables are, but with what we refer to as a case or as an individual or as an observation. These are the objects described by a set of data. Or in other words, if you think about a set of data, it's just a matrix or a spreadsheet. So you've got someone's education, their income, and that's really all we need for this class, but you could add more things at higher levels. But let's just say their education and their income in a spreadsheet. So a spreadsheet that's got n rows and 2 columns. The observations would just be the rows. They're the basically units of our data set. Often that'll be people, but it can be other things. It could be firms, it could be countries, it could be municipalities, it could be any manner of things. It could be hospitals, whatever you want to put in there. But it's basically the key unit of a given data set. Sometimes you have multi-level data sets where you've got different kind of levels of units, but we won't deal with that in this class. So that's what individuals or cases or observations are. It's oftentimes very convenient to think about them as rows. So the properties that are represented by people's scores or, just any observation scores are different variables. So a variable is basically a property or a quality that we care about, which varies across individuals. So for instance, in the example I was just giving, education and income would be variables. And we typically think of those as columns. And by the way, you can have it done totally differently, where individuals are on the columns and then the variables are on the rows, but almost no one organizes their data that way. For pretty obvious reasons. It can make it hard in that scenario to then figure out like how many variables you have typically. And it's also just an inefficient use of space, because usually we have many more individuals than we have variables. And so in a regular way that we kind of view space, we want it to be a little bit easier to see all the variables right at the top, and then we don't necessarily need to see every individual at once. But that's kind of an aside. So variables fundamentally are just qualities or properties that vary across individuals, hence the term. And here's some examples given before. So I wanted to make this last point here. Cases are concrete. So we can observe a person's income, but a variable is abstract. So we never see education itself floating about in the world. So anytime we see an actual data set, we don't really see the variable as such. Like a variable in a sense is a concept or a property, but actual data includes realization on the variables. Now, we do typically still call those the variables, but it maybe makes more sense to think about variables as, fundamentally these conceptual things that don't, again, have like a corporeal existence. Cases do. So a single person, their income and their education are properties of them. They may not be visible, but they are like fixed actual things. But variables are in principle just kind of the properties themselves, which don't have a real existence. anytime we see someone's actual income or education, we're seeing a realization of it. That's a point that's sometimes important, sometimes not as important. But in general, the simple way to think about it is that in a data set, when you think about going across the rows and looking at one person's score on a variety of different variables, or that realization of k variables, that's a case. And when you look down the columns at all the realizations of one variable or all the realizations of another variable, that is sometimes called a variable, which is a little confusing, but better, it's a sample that gives information about some variable. So variables are properties we care about, and then cases are observations on one or more variables. So here's an example of what I was talking about last time. This is an example of what Stata's background spreadsheet or data matrix looks like. And you can see that this probably looks pretty similar to Excel. So you can see here we've got a variety of different variables. Again, I'm going to use that terminology, but it's important to remember that these are really not, strictly speaking, the variable. They are realizations of a variable. The variable is really just the name of the column. It's the concept or property. And so we can see here we've got make, which is the type of car in this data set. It's called the auto data set that ships automatically with Stata. And we've got the price and the miles per gallon and so on. We also have this list here that indexes all the observations. In some data sets, the data itself will have a unique identifier. So like a person's ID number in a study, or in some cases, if it's like a data set of, let's say, what's an example? Maybe like a data set listing all of the basketball players that have played in the WNBA and NBA since, the formation of those two leagues. The unique identifier would be the person's name, assuming there's no duplicate names. But sometimes data sets don't actually include unique identifier variables. So the way that Stata will keep track of them is it just assigns them a number. That's sometimes useful to know. So in this case, again, you can see an observation is a row. So there was a Concorde car in the data set, and then it had all of these things here. And in principle here, make might or might not uniquely identify the variables. It's hard to tell. It doesn't look like we see any duplicates here, but there may be some. So even identifier variables are like sometimes just mere variables. So for instance, if you do have two people in a data set that share the exact same legal name, then there isn't a, strictly speaking, true identifier variable. You can only identify people by their unique combinations on variables. And unless you have a data error or a data entry error where you truly just have duplicated two people, it should be the case that when you take into account someone's score on every variable, that those things all taken together uniquely identify them. So that's just a bit of background about data. So yeah, you can see here, looking at the rows, these are unique observations, and looking at the columns, oftentimes called vectors. Vector is just a list of things. And in statistics, when we say vector, we usually mean a column list. We also have row vectors, but it's conventional when you say vector and you don't specify that you mean a column. So this is a vector of data here. This is a vector of data. And a list of vectors all in a row, you may know, is just called a matrix. So this is also sometimes called the data matrix. Matrix basically just means a spreadsheet. So that is kind of how we could visualize all this stuff in a concrete case. And I think that's about everything I wanted to say about that. We'll see later on that vectors can also be envisioned as the set of coordinates in space. It might seem weird to think about how we could envision 30 or more dimensional space, but we'll see that it's actually not that bad. So we answered these questions already. So the individual cars are our observations, and the variables are things such as make, price, and miles per gallon. Here's another example. So what are our observations in this particular case? We might want to take a second look at this. We see that this is a data set. We've got something called FIPS, which is basically a way of identifying counties. We can see we've also got years, then we've got FIPS code, and this distinction here you'll often see in messy real-world data. This is a numeric version of this variable. It's not possible to see that from the data matrix, but I just happen to know that because I made this data set. We can see where we've got state, we've got area name. What that is just the actual name of the county and not its FIPS code. Then we've got some variables like civilian labor force, employed, unemployed, and unemployment rate, and there's more to come. So if we look across the rows here, what are our observations? Well, it actually doesn't look like it can just be counties because we have some duplicates. And it doesn't look like it can just be years because we've got some duplicates. But if we take a close look at the data set, we see here like 1001 and year 2000, 1001 and year 2010, then 1003, 2000, 1003, and 2010. So it looks like what this is a data set that's got observations on all US counties in 2000 and 2010. This is kind of a complex example. So we would say that the observations are unique county year combinations because there don't appear to be multiple observations on, say, Watauga County, Alabama in 2000 or 2010. So those would be the observations. And as we noted before, even things that might often seem like they should uniquely identify the observations, like the county or the year, in this case, they don't. And if we look at our other variables, technically these are all variables, but the ones that we think of as like true variables and not just the ID variables would be this set of things here. So that type of information. These are, again, also variables. So the way we identify observations is we typically need to invoke some variable, even if it's just this variable here that represents the number. But usually when we say variables, oftentimes what's meant is the observations on some other set of variables that is not just keeping track of like who is a person or who is an observation, but facts about them. Computer's going a little slow here. So let's talk about types of variables. I don't think I skipped a slide. Yeah, sorry. Computer's just going very slow. Apologies, folks. So let's talk about types of variables. So we'll start with what are called nominal variables. So this is a type of qualitative variable, but I'll come back to qualitative versus quantitative in general. Nominal variables are what are called unordered categorical variables or purely qualitative ones. So what that means is that any numeric values of the variable are totally arbitrary. Some common examples might be race, religion, or gender. We could say, well, if someone is a man, put down 1. If someone is a woman, put down 0. And that's a very common actual coding scheme in reality because it's got some really nice mathematical properties. But in that case, writing down 1 and 0 doesn't have any intrinsic meaning. So it doesn't actually tell us that man is more than woman or vice versa. And in principle, that coding scheme could also work if we had, arbitrary numbers as well. So we could say something like 7 and 8, for instance. And that would mean, the same thing in a certain way. It's just a way of telling apart these two qualitative statuses. But yeah, it's even more arbitrary. You could also say, going back to our original example, you can make male 0 and female 1. And that doesn't have any actual, that doesn't, we're not like changing the meaning of the variable, basically. So that's a nominal variable. Ordinal variables are still, in a sense, qualitative, meaning that they don't really immediately fit with numbers, or they don't immediately have numeric values, and we have to assign them, but they might be orderable. So what that means is that the numbers we assign to the variable just help us basically order the outcomes, but they don't have intrinsic meaning. So let's think about a concrete example. If you have ever taken an exam at a doctor's office and the doctor says, how sick do you feel on the scale of 1 to 10? Notice that for different individuals, those scales are going to vary. And even assume that everyone kind of has the same tolerance to pain, even still, the gap between 4 and 5 and 7 and 8 may not have the same meaning. It's impossible to tell because pain is subjective. So what that means is that everyone that answers that question is going to say, if they say 8, that means more than 7 and more than 5 and less than 10. But the gaps between the variables, the distances represented by the numbers, is not uniform. And so once again, the numbers are somewhat misleading. You can think about that too for something like, let's say, education. So you can write down someone's years of education, but you can also just write down their degree. So you could say no high school degree, trade college, 4-year college, and then like a doctoral degree and master's degree in there. So that's 6 outcomes. And you could assign them the numbers 1 through 6. And we would say that those represent progressively higher levels of education. But it's really not clear that, using our original example, we said 1 was less than high school and 3 was a trade degree. So the difference between those is 2. Is that really the same thing as the difference between a PhD and a bachelor's degree, which would be 6 minus 4 in our scheme? And it's really not clear. Among other things, if we convert those to years of education, those gaps may have different values. So ordinal variables, just if we give them numbers, the numbers only index order, not distance or magnitude. Interval variables, which are the first type of quantitative variable, can be assigned numbers which mark consistent steps, but they don't have a natural zero. And what that means is that addition with these variables makes sense, but not necessarily multiplication. Degrees centigrade is a classic example. So let me give you this here. So let's say if you have like degrees centigrade, basically when you go up 1 degree and then up another degree and then up another degree, these things all mark, in theory, changes in thermal activity that are all the same. But you might remember from high school math or science that 0 degrees Celsius is not the absence of thermal activity. 0 degrees Kelvin is, and 0 degrees Kelvin is negative 270 something, I think 3 degrees Celsius. So what that means is that the 0 in Celsius is not an actual 0, and that means that multiplication doesn't make sense. So let me give an example of that. Let's say you go from 0 degrees Celsius, which is freezing in Fahrenheit, so 32, and then you go to a pretty balmy day in Celsius. So let's say 30 degrees Celsius, which would be very hot, but livable, I guess, for some period of time. So that would be an increase that is actually really hard to figure out because you can't multiply 0 to get to 30. But if we convert that to Fahrenheit, that would mean going from 32 to like 110 or something around that. I can't remember the exact details. But anyways, it's clear that we could multiply the Fahrenheit scale to get there. Or what if we go from, like, let's say 20 degrees Celsius to 30 degrees Celsius? So multiplying 20 degrees Celsius, the temperature, by 3/2, right? So you're going to say in that case, well, okay, we increased by an amount 3/2, but again, if you convert those to Fahrenheit, the multiplicative factor is going to be different. So we shouldn't really multiply these variables because the scale, it just doesn't work because the 0 doesn't actually mean absence of the variable itself. So you might actually know that there's a lot of different variables that work this way. But yeah, it's kind of interesting to note that even very common examples, such as degrees Fahrenheit or degrees Celsius or centigrade, I mean the same thing, follow this rule that multiplication with them is actually kind of a bad idea. Okay, so let's introduce finally the last type of variable that we like, ratio variables. And I'll go ahead and put up the chart here so we can see all this together. Ratio variables have a meaningful 0. And what that means is that numbers in the set are consistent with the rules of multiplication. Income is a good example. And these are variables that we like the best in statistics because they are self-measuring effectively. So for instance, if you have 0 income, that means you have $0. Now, it's not that realistic, but if someone reports they had actually 0 income, and let's say they live in a kind of pre-capitalist society and they actually don't earn money income, that's meaningful, right? It doesn't mean something other than the person had 0 income if we define income as money and not goods in kind. So we'll later talk about discrete and continuous ratio variables, and we can also talk about discrete and continuous other types of variables as well, but the distinction for ratio variables is the most important. So let's actually talk about that now. And sorry, I'm going to actually fix this here while I'm thinking about it, but we need to make this have an animation that comes next. So pardon me for this. Sorry about that. So let's talk about continuous and discrete variables. So this is a distinction generally within types of quantitative variables. So it's not directly related to the distinctions we just went over. Continuous variables are those that can take on an infinite number of possible values. Discrete can take on a finite number of values. So let's think about that for a second, because that might seem a little confusing. So continuous variables, when we say they can take on infinite possible values, that might seem hard to imagine. But let me give some concrete examples. So height would be one, so would your weight, and so would maybe the years you've been alive, or sorry, the time you've been alive, not years. So notice that when I'm saying these things, height, weight, time you've been alive, I'm saying them in a very general and abstract sense. So why does that mean they could take on an infinite number of possible values? Well, what that means, and that's not the most precise definition, but it's a good way to think about it. What that means is that in principle, you could keep measuring those things to more and more and more precision. So for instance, if you could come up with an instrument that could measure someone's height to the nanometer, and then let's say you measure someone's height to the nanometer of a nanometer, something like that, then we would say, well, why would you ever stop, right? I mean, apart from reasons of practicality, but like, is there any reason you have to stop? In principle, no. And the reason for that is that there's like the nature of height itself, it's not self-limiting. There's not a reason that height can no longer be measured past a certain point, apart from human measurement error. Discrete variables, though, only take on a finite number of values. So one example might be something like the number of kids you have. And the reason for that is that kids don't come in halves or thirds or whatever. And I can already hear someone saying, well, what about an infinite number of kids, right? And, you would say, well, okay, I guess that seems like that would be very hard on that family, but that is possible in a sense. Or what about number of people, right? So maybe number of people could somehow multiply to infinity. But those numbers are actually called what are called countably infinite numbers. And so when we think things are countable, meaning that they come in distinct chunks. So like we know the distance between two of them will always be one, or it'll always be a half or something like that. Then that means that, the number basically has different properties than one that's continuous. The primary difference is that measuring a discrete variable past a certain level of precision is pointless. So for example, if you think about something like the question on a survey, how many days in the past week have you felt depressed? That's a discrete variable because it can only take on values between the numbers 0 and 7, right? So only 8 possible values. And there's no sense in measuring it further because we didn't ask them how many minutes or how many hours. So and that's a different kind of conceptual object. So number of days or number of kids, something like that, can only come in one case, potentially countably infinite numbers. In the other case, it's just got a finite limit. I wanted to make some fine points here because these can come back to bite us. So first of all actual data are discrete because they're finite, meaning that you don't ever actually observe the continuous part of a continuous variable. But some data are realizations of continuous variables, meaning that they come from variables that could in principle take on any number of values. And that is important for how we model those variables. Also, all actual data are discrete because of the limitedness of measurement systems. So the fact that you only have a fixed set of observations and the fact that they can't be measured past a certain precision, those make the data, in a sense, members of a discrete set. But the variables themselves, again, could be continuous. And the distinction matters a lot. By the way, continuous variables don't need to have an infinite range, so they could be bounded between 0 and 1. And this is one of the hardest ideas to get in math, I found, even though it's, in a way, quite intuitive and beautiful. But let me illustrate the point this way. You might say that there's a limit on human height. Let's just say, for instance, that no one will ever be taller than 10 feet. That's pretty generous. But height is still a continuous variable in that someone's height could be 3.14159 da 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 da, in feet or meters or whatever. And there's not any reason in principle that we stop measuring, right? Again, it has to do with the instrument itself. So even though it's bounded, it can still take on infinite possible values. What we saw before, this is kind of weird, but even variables that could potentially go up to infinity or go up to extremely large numbers, if they don't take on like infinitely precise values, or they can't take on further and further precise values, then they are discrete. So that's a little bit of a confusing idea, but it's important. So here are some examples. Again, height, age, job tenure will be continuous, and discrete examples might be number of children, or your hourly wage, or semesters of school. And you might think hourly wage, well, that's usually a decimal number, right? But remember that apart from banks and other financial institutions, no actual person counts income in amounts that are smaller than a cent. Many financial institutions do, but someone's wage is always going to be rounded to the cent. Same with semesters of school. You could think about that as like, well, that's time, right? Isn't time continuous? But if we ask the question as semesters, then that's only going to come in 0 through infinity, which is countably infinite. Okay, so let's talk about visualizing these things. We'll actually start with the easy stuff with qualitative variables. So let's revisit an old friend, the pie graph, and I'll show an example in a moment. Pie graphs use central angle measure. So basically the kind of width of a slice, although it's not really a constant width, but the angle that a slice represents to convey the relative frequency of observations in some chunk or in some other chunk. Basically, when I say chunk, I mean a possible value of the variable. They work really well when there's relatively few categories, but they don't work so well when you've got many categories. So you can see here that for race, using data from the Current Population Survey 2019, and I'll always print the information that I draw these from down here. This doesn't look too bad. It looks a little bit amateurish, and it's maybe a bit hard to kind of make comparisons, but it's not terrible. But this distribution of occupations in the US looks pretty bad. And the reason for that is we've just got too many possible values. So it's sort of not really summarizing information well, which kind of defeats the purpose of a graph. A thought question for you, and one I'll just answer now in the interest of time. Could we just delete some of the categories from the right to make it easier to read? And the answer to that is actually no, because we would either be left with white space, or we would just be redoing the pie graph, but for, say, the distribution of occupations between these three here. So out of these three occupations, what are the relative frequencies? And that would result in a different graph. So there's not a really easy fix to this problem with pie graphs. What we'll often want to do instead is use bar graphs. So this is the same data as this last slide here. So see these occupations here are now represented here. And what these do is show for a given category, and category is another way of saying one of the possible values of a qualitative variable, we'll have on the x-axis, and this is the x-axis even though it's going vertical. X-axis in this context just means the axis where the sort of like input is. And this is a bar graph is an estimate of what's called a probability mass function, and the inputs to the probability mass function are the possible values, the outputs are the probabilities or percents. So we'll come back to that later, but that means that these are the inputs, so they're the x-axis, and as heights, so heights, scare quote here, even though they look like widths, are the y-axis. And so what bar charts do is on the x, you plug in some value, and a value in our class will sometimes mean things that aren't numeric. So here it's possible occupations such as mining or the armed forces or education. And then on the y-axis, you get the probability of someone being there, and probabilities and percents, as I'll stress many times in this class, are pretty much identical for most purposes. That's a little bit oversimplified, but we'll come back to that some other time. And so bar charts are usually the best choice for qualitative data, especially horizontal bar charts like this, where you've got the values ordered in terms of their frequency of occurrence. And the code, by the way, code for all of these cool graphs is in the slides. So Sorry, Google Slides makes it a bit hard to jump out here. But if you come here, you can see the code is all the way down here. And I'll show you how this works, actually. Let's just do this now. So we want to pull up Stata. And this type of code needs to be run from a do file. Anytime you see these line extenders, it's much easier to run from a do file. So we can pull up a blank do file, paste this in, highlight it, and then Command-Shift-D on a Mac will run this. Oh, and we need to load the data first, sorry. So I usually don't include that part. So let's load the data. Data, Jesus, wait, CPS 2019, sorry, folks. Underscore. And oops, now we'll come back here and run this. And you can see that this will take a little while, but it produces the same graph. I have a different scheme here, which is why these look slightly different, but they otherwise look pretty similar. Okay, so I wanted to note some things about bar graphs that we'll come back to in a little bit, but one thing to note here is that this x-axis, as I mentioned before, does not really need to be numeric. And notice that these white spaces here don't have any precise meaning as they would on like a Cartesian plane, where you've got some line y equals mx plus b. The x-axis there is, you know, every bit of it is sort of meaningful, but here these white spaces are just kind of like null spaces. And another thing to note too here is that you can have bar graphs that are bivariate. So we could have here something like education and health services, and then the y-axis could be the mean wage in that occupation. So this is a distributional plot. It's univariate, just shows the possible outcomes of a variable and then their frequency of occurrence or their probability of occurring. We can have bivariate bar graphs as well. For quantitative variables, we often like to use what are called histograms. Histograms are very similar to that bar chart we saw, but there's some key differences. So these also show the distribution of a single variable by putting the possible values on the x-axis and then the probabilities or percents on the y. And one thing that's always challenging with the histogram is we have to think about how wide we want these bins to be. So here these bins, you can see, span 2 years of education. So here we're saying like this right here is the probability that someone had between 0 and 2 years of education, probability that they had between 2 and 4, between 12 and 14, and so on. And you can see here that these are inclusive. Well, you can infer that these are left-bound inclusive. So this is 12 and 13, this is 14 and 15, and so on. And that might seem a little bit awkward because it's not clear from the graph. That's a problem that's worse when there's fewer values of the variable. These are oftentimes a little bit tricky to interpret because they, again, like they're in 2 dimensions, but the point here is that you do want to think about these as being just a representation of one variable. So possible values of the variable on the x, and then actual observed percentages corresponding to those on the y. So histograms are important to be able to interpret correctly. We've got information about their central tendency, and central tendency means just the most typical value of a set in a sense, or the true value. And those are captured by the mean, median, and mode. We'll come back and talk about those later on. For now, you can think about the median as the equal areas point. So it's the point on the x-axis where 50% of the observations are to the left, 50 are to the right. The mode is the tallest point, and that is the most frequent value. Although the mode kind of depends on how much you bin the data. So here, this would appear to be the mode, but that could change in principle if the height of this thing is less than 2 times the height of this thing, maybe both of these things are here, maybe all of this data is just in the 14 bin, and so maybe that would be the mode. So modes are flexible in that sense, and you can think about the mean as the balance point. So the balance point would be, if you imagine like basically a lever here, where would you place the fulcrum? And in this case, we've got some observations out here that are a little bit far from the center. So we might think that the mean is actually like coming down here a little bit lower than the median, something like that. And so we already answered these questions. So histograms also tell us the spread of the data and the shape, which are are both kind of like informal ways of thinking about the variability of a data set. So we'll make those more precise soon. But for now, you can think about the shape in a couple of ways. The number of peaks or modes, and then also the symmetry or lack thereof, so the skew. And you can also think about the spread in a pretty simple way as the range, so the maximum x value minus the minimum x value. Outliers also kind of, well, first of all, they influence the spread for obvious reasons, but they can also influence the shape as well. Shape is a pretty generic term. It refers to a property of an entire distribution that's kind of hard to summarize without knowing directly the function. But we can describe the shape pretty simply in some broad strokes. So this clearly has a left skew because the data have a tail that trails off to the left. And by tail, we mean parts of the graph where the data are either unusually large or small. And here, it's not even really the case because this goes down to 0, this goes down to 10. The middle does appear to be around 10 or 12. So these aren't really that small. But the idea is that we've got fewer observations down here, and there appears to be a number of observations that are well below the mean and median that aren't matched by like a sparseness over here, because most of the data is clustered over here. So that's one way to think about, the way to think about it visually is just tails. So do you see a tail, a number of observations that are infrequent but non-zero that are in one end of the graph? So we've got a skew here. We've also got apparently a couple of modes. I mean, it's kind of hard to say really. Maybe we would count these two just because it's sometimes conventional to count two modes. We do appear to have one that's pretty obviously the peak. The way you describe the number of peaks, again, you could think about almost all of these as peaks in a sense because they're all taller than the smallest one here. So the way to think about peaks when you actually have discrete data like this is it's usually you want to say you have distinct peaks when one, they're in different regions of the graph. So you could have a bimodal graph where you've got something like this. Or maybe you have peaks that appear in places that are expected. So here this appears to be high school graduates and then trade college graduates and then college graduates here. So this might be a reason to call these peaks, but there's not really an exact definition for kind of complicated reasons. To put it formally, it really only makes sense to think about true peaks or local maxima when you've got a continuous function, and we don't have one here because this is discrete data. So it's kind of up to the user. Let's go ahead and try to interpret this histogram. So what's the center of our data here? Well, we can see here that the modes would appear to be these values here. This is the distribution of hourly wages if someone's an hourly worker in the US from 2019, the current population survey. So the center appears around here. And we can think about it in a couple of ways. So these are the modes. Those are the most visually obvious. If we think about the equal areas point, it's probably a little bit farther over here, but not too much. If we think about the mean of the balance point, it's probably going to be dragged out a little bit further still, because even though we've got a lot of weight here, like if you think about a lever on a fulcrum, basically levers are balanced. We'll come back to this. This is just kind of a physical fact. They're basically balanced when the combination of weight and distances from the fulcrum, like if you think about multiplying them together to get a product, when that's equal on both sides of the fulcrum. And here you can think about basically the weight as being the kind of like number of observations of a given value. And then the distance is just being the distance from the fulcrum. So here you can see we don't have a lot of observations out here. They have low weight, they have large distance. So that would mean that we could place the fulcrum maybe somewhere closer here. And you could really literally think about putting a fulcrum here and saying, like, I would reckon it'd be somewhere around here. That seems roughly right. Hopefully you've done something like that in high school physics. As far as the shape goes, we do appear to have just kind of one general area of peakage, and then everything else, like everything in this band is higher than everything down here. There's clearly a skew. So there's a long right-tailed skew here. If we think about the spread, its ranges from 100 to $0 per hour. And there do appear to be some outliers. So for now, we'll just tag those as unusually large observations down here. We don't really have any lower end outliers because even though these infrequently observed values even though we have them, they're very close to more frequently observed ones, which again is a way to think about outliers. So these are infrequent observations, but they are close to the bulk of the data, whereas these are infrequent and far from the bulk of the data. We might try to look here at a slightly different type of shape. This is the logarithm of wages for hourly workers in the US. We're not going to use logs a lot in this class, but it's important to note for this that this is the same data set as before, just transformed in a nonlinear way, maybe obviously because the graph looks very different. But the idea behind a logarithm is that when you say like the log of wages, for instance, let wages stand in for A, the log for some base B of wages, if we say that that's equal to some X here, so some X here, that means that taking the base B to that X produces back the original outcome. So let's make that concrete. So a common choice of base you might know is 10. And the natural log, the other common choice of base, is Euler's number 2.7, et cetera. So let's say we have log base 10, right? So log base 10 of 100 would be equal to 2, because taking 10 to 2 produces 100. So you can see these are natural logs, by the way, that when we hit upon a wage here, like 3, what this means here is that this person's wage is what you would get if you took the base of the natural log, 2.7, you can just remember 2.7, to the value of 3 here. And you can do that at home, or you can just kind of quickly do a little bit of mental math and say, okay, so 2.7 and change to the 3 is going to be less than 9. So this is probably somewhere around 7 and change dollars per hour. You can do that out if you want. I'll go ahead and just give the exact value here, so around the 2.7, and then multiply by itself, and you'll get 7.29. So that would appear to be right around minimum wage there. So what's the center of the data in this case? Well, here the data look much more normal, and we're going to say normal with a capital N, which is a formal term for what's sometimes called the bell curve shape, also known as the Gaussian distribution. After Carl Friedrich Gauss, the name is Gauss, but we call the distribution the Gaussian as a kind of Americanism. We'll come back to that very soon and spend a lot of time on it. But just note for now that they kind of have this bell curve shape. So they appear to have a mean, median, and mode that are all in the same area, right? The equal areas point is somewhere around here, the balance point somewhere around here, and the peaks are all right around here. And if we bin the data a little differently, you can, like if we bin to this a little bit more crudely, you can see that it would probably have a pretty clear peak. The shape is, first of all, it's pretty symmetric. There's a bit of a left skew more than a right skew, but both of them have some outliers down here that are about evenly far from the data. And when you've got outliers on both sides, but they're infrequent, typically we say the data are symmetric. And then the spread appears to be, in this case, from about 6 to -1. So if you think about taking these values, so I'll actually show you how you could do this in Stata rather than do this on my phone. So we can actually say here, if we come to Stata, oh, and I realized I didn't actually change my screen. So let me change my sharing here. So let's share a different screen. Let's come to Stata. And then what we can do, I'll get Euler's number. I forget how to call that in Stata. Spend a little bit of time. Oh, yeah, we can just, okay. So yeah, Stata doesn't actually let us directly invoke it, but what we can do is just write basically this. So let's show display, oops. We'll say exp to the -1 here. So we can see this takes Euler's number to the -1, and we get this amount here. So it appears that some people said they probably had a wage that was like very near to 0. Probably someone did say that it was 0. We can actually quickly show that in Stata. So someone did report that their minimum was 0. And then you can see we also had in the graph, or you'll have to look at the slides because I'm over there, but we had someone say a natural log of 6, so we can say display exp6. And you can see that this is 400, but that actually didn't look like the highest value in the graph. Maybe the graph just extended there. So we can actually just tell Stata to tell us what that is. So 100, and that looks like 4.6. So if we come back to the graph, we should see that the actual maximum value looks like 4.6, and indeed it does. So that's how we can interpret that. Back here, sorry about a couple of these stupid Zoom things. Okay, so that's this graph. So let's look at some types of histograms. So we've got here 4 types of histogram. We've got a frequency histogram, a fraction histogram, a density histogram, and a percent histogram. We're going to use these most often. So a frequency histogram basically makes it so that the total bar heights has to sum to n. And it might be worth reflecting on that logic for a moment. What that tells us is that when we bin the data, so we come up with these bins here, we're putting people into buckets. So like if you had a wage between, say, 15 and 17, you go in the same bucket. And the idea then is that if we just record the number of observations in that bucket, the total heights here will end up being the total number of observations. So that's frequency histograms. When we come to fraction histograms, the same is true, except we just divide this axis basically by the number of observations. By the way, these E things here, you might remember, these just tell us to exponentiate. So this is basically saying, like, this is, 1.0 times 10 to the 4 here, because we've got very many observations. So instead of just writing out, say, like 100,000, or sorry, 10,000, losing my mind. So saying 10,000 here, it just writes out this here instead of, like, this could be written the same way as well, except to the third. But Stata's default is to start switching around the point of 10,000. So here, this just divides by the number of observations. So what that means then, of course, is that if each of these represents some fraction of the data and everyone goes into some bin, that means the total fractions have to add to 1, representing the total. The density histogram is a little different. I'll mention it because we will come back and talk about density a lot. But density actually forces the area of the bars to sum to 1. Now you can see here that the shape of this histogram actually does not change from all the others. So all we're doing is scaling this a little bit differently. So it might not be obvious, but if you added up all of these heights here, you would see that we come to 1. So this might appear to just be scaling this differently, and indeed, in a way, it does that. The exact scaling factor is we basically take the width of the bucket, and then we take the number of observations and then scale by that, which is maybe possibly confusing. And really, from the standpoint of this, we're just scaling this by the width of each bucket. But why do we care about these things? Well, continuous variables, their true underlying distribution is best described by what's called a density curve, or a probability density function, to be technical about it. And that is a graph where the height is like not directly easy to interpret, but the area under the curve for a part of it is interpretable as a probability or a percent. And so sometimes we like to do histograms that look like that. I'm personally not a giant fan of these because this is not actually a smooth curve. It's a histogram. It's basically a discrete function here. So this scaling here doesn't really change a lot, and it makes it more confusing, I think, for most people. So I would recommend, best of all, is the percent histogram, because most people find percents more intuitive than fractions, raw frequencies, or densities. We'll mostly use these ones here. That said, when we come to smooth graphs, like actual population distributions instead of sample ones, we will talk about density curves, and there they'll make a little more sense. And we'll see that there's a way to estimate density curves that actually give us smooth functions in Stata or in any software. There's several ways to do it, but the one we'll talk a little bit about is what are called kernel density estimates. But those look different than these. They produce smooth functions. So then it makes more sense to put density on that axis. One thing I wanted to point out here too, so density histograms, again, these in a way are getting us closer to a smooth curve describing the population, but the problem is that they're still histograms, so they're still estimated from discrete data, and we can't, like, a histogram fundamentally requires us to bin the data, and we put every person into one and only one bucket. And so putting density on the y-axis doesn't really change the matter. But I will mention that what density is probability per unit. So the reason that these areas under the curve here are probabilities is that this is probability per unit, but then the area we multiply by a unit. So we get probability as a result. If you think about y being probability over units times a unit, the x, you just end up with probability. We'll talk more about that later. And one way that we can come up with like histograms that look a little bit more like smooth functions is that we can have, in this case, a density histogram that's got equal probabilities here, but different widths. And you can see that this looks a little bit more like a smooth function. It's maybe a better guide in some ways to the reality than that other histogram. But the problem that both of these things have is they're trying to describe a smooth population distribution that we fundamentally don't know. That's what statistics is about. We'll say much more about that later on. But the way to interpret this here is that you can interpret these areas as probabilities. So here you can say we estimate from the sample, this is just sample data from the CPS, like this height here appears to be about 0.013. This is 10 here. So we just move the decimal over 1 when we say 0.13, which is 13% as a fraction, or a decimal, I mean. About 13% of people had a wage less than or equal to 10. And if we check that, I'll show you in Stata. We check that in Stata here. We can do this in a couple of different ways. Probably the simplest way is to summarize the wage variable and then write detail. And you can see here that about 10% of people had, in this case, a wage of 10 or less, and about 25% had a wage of 13 or less. So that means that the people who had 10 or less had to lie between 10% of the data and 25%, and that's probably pretty good. Another way to do it that's slightly more exact is to just write this. So count if wage 1 is less than or equal to 10, and then count if, we'll say count if wage 1, well, we could just say this is the number of people that had values on that variable, people that weren't missing. So we can write display, which can be abbreviated this way. And you do have to take out commas in Stata. So display number of people that had a wage less than or equal to 10 over the number of people who recorded a wage, and that's 13%. So that's how our probability histogram showed us the same thing. So let's go back there. Sorry, folks, I'm having some trouble sharing the correct screen here. Oh, screen sharing is paused. Give me one moment. Let's just try to share the desktop. Okay, here we go. Sharing the desktop here. Oh, it's because we were full screen. I apologize. Okay. So let's talk about some differences between bar graphs and histograms, which are kind of important. Here is a key difference between a bar graph and a histogram. First, the x-axis does not really need to be numeric for bar graphs. So here you can see I use that information on the distribution of wages, but in this case, I binned people into low, medium, and high wage, and you can see how I did that here. That's arbitrary. It's not that meaningful. But notice here that the x-axis is not really numeric. The gap between medium and low is not the same as the gap between high and medium. There's not really a numeric meaning here because these are evenly spaced, but the values these represent, sometimes they may not exist, but here they exist, but they're just not constant. 2, the white space is not meaningful for bar graphs, but on the distribution here in the histogram of wages, white space, which doesn't look like there's a ton of white space here, but there is almost a little bit, means that there are no observations there. And the reason, again, is that these are basically types of graphs that are fundamentally different sorts of objects. This graph here, this bar graph in this case, works really well for discrete data. And it doesn't even necessarily need to be used for discrete data. You can use a histogram for discrete data, but if you're going to use a bar graph, it should be for a nominal variable, an ordinal variable, or a true quantitative variable that doesn't have many observations or many possible values. So it's highly discrete. And in those cases, what we're doing is basically estimating what's called the probability mass function, which is a type of function that tells us the distribution in the population for a discrete variable, or one that's just not a numeric variable. And that's different to a situation where we've got a function that describes the distribution for a true quantitative variable, and that's what's called a probability density function. And those are better approximated by histograms. Okay, so here's another kind of example of the differences I wanted to talk about. Bar graphs also work well for bivariate relationships if you have qualitative predictors. So notice here that this graph, this bar graph, tells us actually the relationship between two variables. So we've got someone's union status, not a member and a member here, and then their hourly wage on the Y. We can see that union members are paid significantly more per hour. So in this case, you can see that the second variable is on the Y, the first variable is on the X, and that is fundamentally different to the types of graphs we were looking at before that show us distributions of just a single variable. There is a limitation here. There's several, but one of them is that this might imply that the number of union members and the number of non-members is the same. Actually, this is a ratio of about like 10 to 1 or 9 to 1 non-member to member. So this bar graph doesn't really fundamentally communicate that, which is just a limitation to note. So in general, histograms are more limited for that purpose because they basically require us to show the entire distribution of two quantitative variables. So notice here that this bar graph doesn't really show the distribution of the X variable very well. It shows the conditional distribution of wages, but not the distribution into member and non-member, or sorry, non-member and member. Histograms basically require us to show that, or else they're not really doing their job. So generally speaking, to show something like the joint distribution of two quantitative variables, so like the probability of observing someone who's got a father that's got 12 years of education, or between 12 and 13, and a respondent who's got between 12 and 13, so which is this spike here, we would, or maybe that's 15, it's a little bit hard to see. These are hard to make. I had to make this in Python. But basically, these are harder to plot because they require a third axis here. This should really say density, a third axis for density here. Although I suppose that, well, this really is percent. Forget that, that's not a big deal. I should have converted this to a density, but it's not a big deal. So basically, this type of graph can work well to show us the joint relationship between two variables here. But they're kind of hard to make. We can't easily make them in stata. And in general, histograms don't really have the ability to show us anything more than the joint distribution of two quantitative variables. They're just not adequate for showing us things like the relationship between a quantitative variable, quantitative outcome, and a qualitative predictor. So when we look for ways to represent the relationship between two quantitative variables, a scatter plot is usually more effective. A couple more caveats here. So practical advice on choosing between them. Don't use a histogram for qualitative variables. It will look like this. This is a histogram for religion. You'll see that almost all real-world data sets assign numeric values to the outcomes of qualitative variables, but that does not mean that they are meaningful. And you should avoid using histograms like that. So this is a histogram for religion, but the numbers assigned to religion on the general social survey from where this comes are not meaningful. So the x-axis here is not meaningful. Of course, you can adjust a histogram and its data to make the x-axis not have numbers, but then you're just making a bar graph by hand, basically, which you shouldn't do. Don't use a bar graph for quantitative variables unless you've chunked the variable into buckets. So remember that bar graphs assume that the data are at a maximum really highly discrete quantitative variables, and usually it assumes that they are qualitative. This is trying to do a bar graph for wages for the CPS, but notice that this is a giant black bar here because this is writing down every number that there is between 0 and 100. So the problem is that this is expecting highly discrete data, and it gets the data that are pretty close to continuous because every number between 0 and 100 is represented here, which still makes them discrete, but not super discrete. So what that means is that this is not binning the data in any way, but we usually want to try to bin data, or else we're just going to end up with a graph that's really hard to look at. And so, again, part of the reason is that we are approximating the distribution of a variable, which in the population would be, wages technically are a discrete variable, but again, they're a discrete variable that's close to continuous. And so this is just not a really good choice here. So in general, even if you have a discrete quantitative variable, it's still probably a better idea to try to use a histogram so that you can bin the data, because it might be technically discrete, but in practice close to continuous. And that's what's happening here. A couple of ending points. So stem plots. You should know how these work, but they're not a big area of focus for us. These are basically crude histograms turned on a side, but they're easier to misuse than histograms and harder to understand. So what these do is show us here, this is basically the leading digit. And so you can see here, this is for highest year of school completed. This is a histogram turned on its side, and this is the stem plot. Notice that they have the same shape. But note here that you have, like in this case, these zeros here because we have 0 through 10 here, or 9 actually. So this is basically in the tens digit, and then this is in the ones digit. So this represents 4 observations with 0 years of education, 2 with 1, and so on. And you can see here that these look roughly equivalent. But the problem is that, one, when you've got any large number of observations and you have to write out all of the numbers, so this here means 3 5s were observed, this means however many 6s were observed, it starts to not look so great when you have these really long strings. And I actually had to reduce in the GSS the education to less than 10 because otherwise there's just way too many observations. So stem plots look a lot like histograms. They've got possible values here on, well, partly possible values here. You sort of have to infer that this is 1 by looking at the numbers, which is also potentially confusing. You have to infer that this bucket represents the 2s by looking at this here. But it does put the possible values on the x-axis in the general sense, and then the relative frequency of observations is just represented by the number of times you write down the number, which is basically making it into a height. But there are a variety of reasons to not necessarily use these. But you should know about them because the book does mention them. I wanted to end with some caveats. So time series plots. You could subtitle this part of the discussion, "Not everything is a histogram." And that's a common mistake that people make once they learn about histograms for the first time or recall what they are, is they start thinking everything is a histogram. Unfortunately, there's many things out there that might look like histograms but aren't. So you might want to quiz yourself, is this a histogram? And I hope you'll pause and think about that here. The answer is that it's not. This is actually effectively a bar graph. So it's a time series plot, technically. But time series plots and bar charts are actually really similar, and it's useful to consider that. So a time series plot is basically a bivariate bar graph with x equal to time right here, and then y equal to some statistic, in this case, the % rate of unemployment, for some other variable y, unemployment rate. And you can see here that I wrote a time series plot, but then I had Stata also show a bar chart here underneath, and then I just combined them. And you can see that they match up perfectly. So basically here we've got this bivariate bar graph, and that's fundamentally what a time series plot is. We've got a two variable relationship. And you could omit either the bars or you could omit the line if you want. It would show the same information. But is that a histogram? No. So what happens when we actually plot the unemployment rates? Those were for Wisconsin from 1976 to present, by the way. Notice that the shape here looks entirely different. So these two shapes, that and this, don't look the same. You can actually make a connection. So you can see this spike here associated with the COVID layoffs is that outlier here. And this spike here associated with the Volcker shock and this spike here associated with the 2008 great financial crisis are probably these two here. But those are showing up as big x-axis values, not big y-axis values. You can imagine turning this on its side, and then in a sense, you can start to kind of infer some of the information, although it still doesn't really help a lot. The point is that that last graph that we just looked at is not a histogram because it doesn't show the univariate distribution clearly. It fundamentally shows a bivariate distribution. A histogram, however, shows the univariate distribution as its primary purpose. So these are values of the unemployment rate, and then these are the relative frequency of observations. This type of fine distinction is key to really understanding data and its representation. And you'll maybe be asked a question like this on a quiz as a bit of maybe a bonus question. So that's where we'll leave off. There is some optional material here. I'll just show you some fun stuff to look at. So you can graph data in all kinds of wacky ways. Here is one of the classics, W.E.B. Du Bois. And he came up with some really cool ways of representing data when he was, well, he actually lived an extremely long time. I think he was almost 100 when he died. Lived up through the 1960s, I think, and was born not long after the Civil War. But anyways, here he's making data from around the turn of last century. And these are a little bit hard to read. You can take a second and look at them if you want. But they basically show different ways of looking at the distribution of people into regions. And then this is a pie chart, but it's kind of fun to see it made by hand. By the way, you can get a book of his illustrations that is a lot of fun to look at, nice coffee table book. By coincidence, my dad got my brother a book like that for the holidays this year, actually, just by coincidence. I thought it was kind of funny because I use this slide every time I teach this class. But yeah, check out that book if you want a nice coffee table book with some sociology. Here's a bigger picture. You can also make cool graphs called a choropleth map, which is a tongue twister, but it's basically a type of map you've probably seen very often. This is basically a bar graph, except we don't have a real x-axis here. We actually have like a two-dimensional x-axis space. You can think about this really in like polar coordinates almost. And then certain regions of that two-dimensional space have different levels of color, which really makes this in a way like a three-dimensional graph in a sense. We're using different shading or filling in to represent in a two-dimensional space some third dimension, which is in this case 30% of people. What actually is this? I'm forgetting now. Sure, totally blanking on what this is. Percent of total farmland in multiple units. Yeah. So this is kind of a cool thing here. So you can see again, there's like a two-dimensional space that's not exactly got a linear shape, and then we're showing the height, which basically represents these things here. This is from Harry Haywood's book, and part of the point of showing this is that Haywood was actually a lifelong communist and a labor organizer, and one of the most prominent Black politicians of his time in a way. He also lived a super long life. Yeah, but he also found time to write a book where he did some pretty fancy data visualization as well. So showing that there's a lot of cool stuff you can do with it. Speaking of which, here's a picture of Vladimir Lenin, and you know, maybe a bit of a better known figure in some ways, obviously one of the most important politicians in the 20th century. And someone that had a really keen interest in statistics. He actually wrote quite a few works that are, I wouldn't say pioneering works of statistical genius, but show a really strong ability to use descriptive statistics in a way that's would, you know, be make him a standout member of our class, let's say. And this is a pretty interesting thing happening here. This is actually kind of like a bivariate bar chart here. You can see basically for different types of land holdings here, then you can see the percentages of total in what are called, I'm going to mess up the pronunciation of this, but basically this is a type of sort of land unit. Finally, I'll show one more thing here. This is what's called a Nightingale plot. Oh, I don't think I put this up here. It's in the description. But basically, this is showing kind of over time, like over a cyclical amount of time. So you can see here 1855 to March 1858, 1854 to March 1855. So when you've got a certain amount of like basically recurring events, so you can see here that these months recur, and then you can see different kind of causes of mortality here. So the blue segment represents death from preventable diseases. The black line shows death from all other causes. And then I think the red area, what does the red area show? The red area shows something else. The red wedges show deaths from wounds. Okay. So and that's basically showing by month. So these are kind of a fun plot as well. So none of those do you need to actually use in our class, but I thought I would just show that you have some options and that lots of pioneering social scientists have used, some unusual ways of graphing data. They've gotten really creative with it, which hopefully gives you some motivation to keep doing that together. So that's where this lecture ends. Thanks everyone for watching.